Okay, so I'd like to start by thanking the organizers for um, the invitation to speak here and for putting together this online conference. Seems like a really good model for what these online conferences can be. Hopefully, it doesn't become a replacement for in-person conferences in the future. But still, for these times, I think it's a really good way to continue kind of thinking about math. Okay, so first off, this is all joint with Grigoriev, Ramidi, and Boris Okun. Okay? So I'm going to start by telling you about a theorem of Luke, which will give you, it's kind of motivation for the project that we're doing. It's going to tell you the setup that I'm going to use throughout the whole talk. So here's the setup. You take a finite complex. You let gamma will be its fundamental group. And we always make this assumption on gamma that it's residually finite. So this means it has a lot of finite index subgroups, roughly. So what it really means, what it implies is that I can find this, what I'm going to call a nested chain, usually, of subgroups. All of them are finite index. All of them are normal in the group. Gamma I plus 1 is contained in gamma I. And they intersect in the trivial group. Okay? So then what you do is you look at the finite covers of X. So these are going to be regular covers of X since the subgroups are normal. And you think of them as getting, somehow, since the subgroups are getting smaller, the covers are getting larger, and they serve as better and better approximations to the universal cover of X. So then the game that you play is that, well, I'm going to take like a kind of classical invariant of these spaces, see how they grow in the finite cover, and maybe, or if you're lucky, they somehow converge to something, some invariant of the universal cover. And if you can do that, then you can learn something hopefully interesting about that invariant on the universal cover, or you can use that invariant on the universal cover to tell you something interesting about the spaces. So Luke's theorem is that this works very well for the usual Betti numbers, something like real coefficients here, of the finite covers. So you have to normalize by the index of the subgroups, because if you don't do that, these things tend to blow up to infinity. Once you normalize, they're going to be, well, at least each term will be they'll be uniformly bounded. So the first kind of amazing fact is that these numbers converge. So there's no reason to think that they should, okay? And the second thing is that they converge to something interesting, the L2 Betti number of the universal cover with respect to the, that should be a gamma, so that's respect to the gamma action, okay? So I won't talk about the right-hand side at all in this talk. It's some measure of some cohomology groups on the universal cover. But for what we're going to look at, you won't have an analog of this. So we're just going to look at modifications of the left-hand side, and then and see what we can say there. Oh wait, one thing before I go on. So the first something that's kind of hidden here is that I could have chosen two different normal chains, that finite index normal chains, and there's no reason to expect that you get the same answer. It's kind of a related problem too. There's no reason to expect that these numbers converge to a limit. So that's just something that we're going to have to deal with. Luke says, that it doesn't matter in this example. You can take any two chains that you want and you get the same answer. Okay, so one more thing is that X is always going to be in a spherical space for us, which means no higher homotopy groups. What it really means is the homotopy type of X only depends on the fundamental group. So you're really just, I'm going to now look at the Betti numbers of G, or the Betti numbers of the gamma I. For that, all that I mean there is the Betti numbers of a spherical space with that fundamental group. Okay. So so now here's what we do. We take a residually finite group. You take a sequence as above, and you just define the mod P L2 Betti number Analogously to Luke's definition, you take the Betti numbers of the gamma k's with FP coefficients, not with real coefficients, and again, you normalize by the index so that it makes sense. So as you can guess, I had to put a Lin soup here because we don't know that these numbers converge at all because we don't have an analog of the mod P L2 Betti number, or this is our mod P L2 Betti number. We don't have an analytic invariant on the universal cover. So another thing which I kind of said was nice in the L2 in the usual case, which we don't have, is we don't know that it depends on the chain. But I'm not going to bother putting. So this isn't completely well defined, but I'm not going to bother putting the chain in the notation. There's definitely been work by a number of people to give analytic interpretations to these to this growth of mod P Betti numbers to get it like an actual analog on the universal cover, but in general, we don't have this. Okay, what we do know, I mean, the only thing that I really know at this point is that we have, since any space has more mod P homology than rational homology, you can say that whatever these things are, they have to be larger than the, this is just the usual L2 Betti number. So we can say, sometimes we can do some computations knowing the original L2 Betti numbers. So another thing that helps with computations, which maybe I should go back here. So if I take the alternating sum on the left-hand side, so you take the alternating sum here, then you get just the Euler characteristic of x, because that's multiplicative. Okay, so you know that these things compute the Euler characteristic, and that lets you, in some cases, compute what they are. But in general, it's a hard question to work these out. So maybe I should, okay, so let me just give you one example without writing it out. So if I give you like the fundamental group of a closed surface, for example, if I take finite covers of that and I tell you that's an index K cover, well then, you can work out exactly what the homotopy type of that cover has to be. So the only and then, you can do the same thing for a graph if you want to do this for a free group. In both cases, there's only going to be interesting homology growth in dimension 1, and in which case it's just controlled by the Euler characteristic. So though you get concentration. So kind of what's nice about using these mod P Betti numbers is that once you go to the limit, a lot of things go to 0. So sometimes that makes some computations easier. Okay, so here's a conjecture to kind of show how, in general, these mod P L2 Betti numbers are hard to compute. So it was a conjecture of Luke. I'm not sure exactly when it was made. It was published in a paper in 2016, somewhere around then. But he said, maybe these, mod P Betti numbers are always the same as the rational L2 Betti numbers. Of course, they're going to be different when you look at specific spaces because, you can just have spaces with more FP homology. But once you go to the tower and do this whole limit argument, maybe they limit to the same thing. So this will turn out to be too optimistic. In general, that's kind of the first part of this project is finding a group with more FP homology growth than rational homology growth. So let me say, it is a theorem about groups. First, if you want to just look at spaces, there are easy counterexamples. And I'm only going to bring this up because these come up later when we construct our examples. So if you want a specific example, you can take a 3-dimensional Moore space for Z mod P. It just means you glue a 3-disk onto a 2-sphere by a degree P map. So that's simply connected, and it has more FP homology than rational homology. Then you can take a wedge with a circle. Then you get now you have a space that has fundamental group Z. You go to the universal cover. It looks like a string of these Moore spaces strung along the real line. At any finite cyclic cover, you have a bunch of these Moore spaces glued together along a circle. So you have a lot of FP homology, but no rational homology growth. and you can basically do the exact same thing if you want to make an aspherical example, but now the covers don't limit to the universal cover, they limit to some intermediate cover. So it's really, if you kind of loosen everything, you get easy counterexamples. And it'll turn out our counterexamples aren't that hard either. So at least hard to construct. Okay. Here's some more conjectures. So now we're restricting to not just groups, but we're restricting to fundamental groups of closed aspherical manifolds. And again, as I said, the setup is everything is residually finite. So just, kind of stick that in. Actually, for us, I mean, for the Singer conjecture, and Luke, you don't need this for the Singer conjecture, but I'm gonna just imagine that it holds. Okay, so Singer's conjecture is that the ith L2 Betti number, again, I'm saying with rational coefficients. So what you should think of is this is the L2 Betti number of the universal cover. In odd dimensions, it's saying there's no linear rational homology growth outside of the, out in any dimension. And in even dimensions, you have exactly one dimension where you see this, linear homology growth. And in that case, you're guaranteed to have some just by the fact that these numbers do compute the Euler characteristic. So if you have non-zero Euler characteristic, you should get something in some dimension. So this is, you can think this is what we saw for the surface case. We saw if I take a two manifold, which is closed and aspherical, then I do get usually something in Betti 1, but nothing in Betti 0 or Betti 2. And this is saying this middle dimension phenomenon is true for all manifolds, or aspherical manifolds. So the other one is really about odd dimensional manifolds. So I'm assuming here that n is odd. Otherwise, n minus 1 over 2 doesn't make too much sense. So this was a conjecture, which I'll give a little bit more history of soon. But this was again made more recently. Singer conjecture was made in the 70s. I think this was started around 2007 or something. So this is a conjecture about where you're in the odd dimensional case, and as we said, you have a sublinear homology growth in all degrees. So then Luke says, well, now instead of looking at rational homology, look at integral homology. We know that what we said is that the z part, if the Singer conjecture is true, the free part of the z homology is grows sublinearly. So then Luke says, look at the torsion part. And the conjecture is that, again, that you shouldn't have any torsion growth. Now I have to be a little, so there's no dimensions anymore. So what you do is you just take it's kind of a rough thing, but you take the entire size of the torsion and then take the log. That's kind of the analog of taking the Betti number. Again, normalized by the index. If you're not in this dimension n minus 1 over 2, you should get 0. And actually, the limit should be 0. Okay. So where did this really come from? So Bergeron and Venkatesh really made a conjecture about very specific manifolds and specific chains. So they were looking at arithmetic locally symmetric spaces, and the covers were supposed to come from congruent subgroups. I think they originally had only closed locally symmetric spaces, but later on, there are now conjectures about like SLNZ or hyperbolic manifolds which are finite volume. So they were, I'm not the person to tell you why they made this conjecture. It was motivated by certain heuristics in number theory. But Luke is really conjecturing that this homological vanishing of torsion growth isn't really a number theoretic phenomenon. Maybe it's just something about all aspherical manifolds and all chains. Okay. So in both cases, so I think what Bergeron and Venkatesh were more interested in was not vanishing of torsion growth, but actually non-vanishing. So they also predicted, and Luke predicts this too, that if you are in this certain dimension, this middle dimension for homological torsion, then they can tell, then sometimes this number is greater than 0, and it should limit to what's called the L2 torsion of the fundamental group. Okay, and this is again an invariant that you get from the universal cover of the manifold. So, and the general picture is that Luke's approximation theorem should have a torsion analog, and it should be given by this. And sometimes you can compute what this is. So, for example, this is greater than 0 for all hyperbolic manifolds, or like SL3Z, SL4Z. In this case, it's roughly, it's a constant times the volume of the manifold. So what they're saying is that torsion the growth of torsion should be roughly proportional to the volume of the hyperbolic manifold. Okay, let me go on. Okay, so what we're going to show, sorry, let me go back. So what we're going to show is that these two conjectures, we can't really compute anything, but we'll show that these two conjectures are incompatible. Okay, so one of them's got to be false. The reason for that is together they imply an FP version of the Singer conjecture, which is exactly the statement that if you take an N manifold, have residually finite fundamental group, the mod PL2 Betty numbers should vanish outside of the middle dimension. So this is, because FP Betty numbers are bigger than rational ones, we know this is strictly stronger, but together with Luke, strictly stronger than Singer, but Singer and Luke imply this one. And then maybe I should say, together they only, Luke's conjecture is really about odd dimensional manifolds. You can just state the Singer conjecture in all degrees, but really they just imply the odd dimensional statement. So here's how the proof works for this implication. So it's, I don't know anything about torsion, but I knew, I know the Kunith formula and I know universal coefficients. So suppose that there's a counterexample to this FP Singer conjecture, but we know that the Singer conjecture holds. So we get this strict inequality. This one would be 0, and this one is non-zero. And if you want, I don't think this is important. You can always assume it's above the middle dimension, okay, by duality. Okay, so what happens then? So where does this FP homology come from? Well, so it comes from, by universal coefficients, it comes from 3 places. It comes from this, or it comes from Z mod P to the K summands in, either in dimension I or dimension I minus 1. Oh, sorry, this is a typo here. So I should have in dimension I or dimension I minus 1 here. So what can happen is that maybe this is Luke's predicted dimension. Okay, we can't rule that out. But if that was the case, then the Kunith formula, so again, you have to be like an odd dimensional manifold. So you take like a triple product, you stay odd. And now this, value, which is above n over 2, when you take products, it moves further and further away from the middle dimension. Okay? So that means that, but then once you kind of move farther away, this torsion argument still works, and you get torsion around where, where you get non-trivial mod P L2 Betty number. So that's it. Okay, so maybe I'll just, explain how this conjecture is probably supposed to go. You might ask, why is Luke's conjecture compatible with Kunith formula at all? And what happens is that the log of the torsion is supposed to grow, but if you look at any like Z mod P or P to the K summand, it should grow slowly. So this torsion is conjecturally supposed to grow, but it's supposed to grow because of large primes, not because of a lot of summands. And there's a lot of experimental evidence that has gone into like computing these things to confirm Berezan and Venkatesh's conjecture, and that the experiments say that these kind of huge primes appear in the torsion rather than lots of powers of primes or multiple summands. Okay. Okay, so that's the implication. This is what we show to be false. So this is our main theorem. So first, let me just say, even so, the Singer conjecture in the FP version isn't known even in dimension 3. So it turns out that once you know virtual fibering, you do get it for a lot of chains, but since we don't know that depends on the chain, you don't know it in general. Though there has been, I should mention, there's been a lot of work on this by a variety of people. I think Caligari and Emerton were probably the first ones to consider this problem in this context. Okay. So what we can show is that in high dimensions, it's false. So, but we only know it for odd primes. So for any odd prime, this FP Singer conjecture is going to fail in odd dimensions bigger than or equal to 7. And then because, again, I only know Kunith formula, you can all work out how I got that one. Okay, so so the manifolds that we construct they come from right-angled Coxeter groups. So they're pretty nice from some point of view. They're PL manifolds, so they're not naturally like, non-positively curve-Riemannian, but they have this combinatorial version of non-positive curvature, which is that they're locally cat zero. Okay. So on the other hand, they're pretty far from being locally symmetric manifolds. So we don't touch at all the Bergeron-Venkatesh conjecture. Again, we can't really disprove any conjecture, but we certainly can't say that this one is incompatible with anything. So here's what we do. Okay, here's the outline. So you first find an example of a group that is a contradiction to Luke's original conjecture. Okay, that just for any group. So we find one that's strictly larger, and you can ensure that this one is 0 and this one is non-zero. Okay. So the group is a right-angled Artin group based on a flag complex with more FP homology than rational homology. Okay, so you can think of this, you kind of take any complex, like for example, this Moore space that I mentioned earlier in the talk, and this right-angled Artin group kind of provides you an aspherical complex that still, you have to show this, but it satisfies like kind of the same weird homology that there's more FP than rational. In this case, you see it when you go to these mod PL two-body numbers. So I'm just going to mention again, by universal coefficients, we know if you have this, so you can take a specific example now, like I don't know, L could be RP2. In that case, this group will have exponential homological torsion growth in dimension 2. I'm only mentioning this because I think this was also an unknown question, whether there was a group where you could have torsion growth in these finite index, normal residual chains. Okay, so the problem is at this point is that these right-angled Artin groups are very far from being fundamental groups of closed aspherical manifolds. So the way that we, then want to, find the manifolds is that we embed these right-angled Artin groups as subgroups of right-angled Coxeter groups, which have nerve of flag triangulation of a sphere. So the reason that you do that is because a right-angled Coxeter group based on a flag triangulation of a sphere has a finite index subgroup, which is fundamental group of a closed aspherical manifold. So you should think these rags are the things that we can compute with, like we can do this computation. And the Coxeter groups are the things that we can construct manifolds with. Okay, I have to work on my aim with highlighting. Okay, so once you have that, we now put into a manifold. That's great. We know how to do that. The crucial point is that if P is not equal to 2, we can arrange that that you see these IFL2 numbers, they're non-zero above the middle dimension of the manifold. So I'm not going to try to convince you that this is the hard part, but it turns out to be the hard part. And it's the reason why we can't do this for the prime two. Maybe just to convince you it's hard. I don't know if this will convince you, but it's very easy to find a subgroup of a closed aspherical manifold group with I L2 number mod PL2 number non-zero for I less than the middle dimension. Because as we said, like free groups have Betti numbers in dimension 1 or surface groups. Okay, so if you can find a free subgroup, then you've done it for the reverse inequality. But so it turns out the hard thing is to find high dimensional mod P homological growth, above the middle dimension. Then what you do is you say, well, I'm going to do so. We have to do some induction and some Meyer-V-Torus arguments. So what's going to happen is this I homology. You do some Meyer-V-Torus, it will either persist, and you'll find that the fundamental group of this also has mod P homology growth in the same dimension, or it gets canceled, and the way it gets canceled is that you see some high dimensional mod P homology growth in the link of some triangulation. So this is just something that, so either what happens is the Singer conjecture is, false for these examples, or you can find some lower dimensional example. It'll again be a right angle Coxeter group, which is, I guess, since we come up with examples in 7, it's either 5 or 3, and it will fail there. Okay, so our examples are kind of non-constructive in some sense. Like we know that there's a counterexample in dimension 7, but as I said, we don't even know it in dimension 3. So what could happen is you just have a counterexample in dimension 3, and you take products of surfaces, and you get to a counterexample in dimension 7. But either way, it's false. So okay, so I think let me see. Yeah, so I have some facts about rags and right angle Coxeter groups, but I think I'm gonna stop here, and I'll see you at the conference. I'll see you in the comments section. So thanks very much for your time.